if you train a model and it has a set of values, and then you try to override those values, it results in very erratic and unstable behavior. The field of reinforcement learning is itself evolving quite quickly, and it's relatively young. Every additional month, it becomes harder and harder to separate thought about the model from thought about I'm interacting with another human being in some senses.
Hansohl Kim is an engineer at Anthropic, where he works on reinforcement learning and AI safety for models like Claude. With experience spanning computer science, biotech, and machine learning, Hansohl brings a unique perspective to building safe and reliable AI. Join me as we dive into Hansohl's journey and explore Anthropic's approach to shaping the future of artificial intelligence. Welcome, Hansohl, to the Getting to Alpha podcast.
Thank you for having me. It's a pleasure to be here.
So excited to have you here. Let's start by winding it back. What was your educational background that led you here, right to Anthropic, in the eye of the hurricane?
I started studying computer science at Stanford in undergrad. Originally, I'd actually been pursuing theoretical physics and then chemical engineering, and then finally took a programming class and absolutely loved it. And sort of naturally along the way, found that of all the different branches I could pursue in computer science, AI at the time seemed the most fascinating and really the most fun. And this was back in 2015, I think. And so from there, I continued to study with a specialization in AI, which at the time didn't really mean neural networks so much. It had started to move in that direction, but it wasn't obvious. From there, after school, I joined NVIDIA, where I worked for about 2.5 years, primarily using machine learning and AI to try to improve their chip design. And then at that point, I actually jumped into biotech as a result of, I think, really the pandemic and wanting to work directly with companies that were working on responses to COVID. That lasted another 3 years, at which point I took a look around and saw that the entire landscape of AI had changed completely, left biotech, and started looking around at labs and companies that I wanted to work at. And I think Anthropic really stood out at the time as heavily differentiated in the type of research they wanted to do and why. And they were pushing very hard in the direction of AI interpretability, AI safety, in some senses, even like a level of AI philosophy, and trying to understand what kind of impacts we might expect from this technology beyond just the bottom line profit. So I can do hyperdimensional math and I can do game theory in the same place, and I can take in very complex high performance computing and distributed systems, and all these things mesh together in ways that you absolutely would not expect, to the point that conversations with colleagues about philosophy are actually fairly common in the hallways, because the intersection of all the different sort of relevant ideas and concepts here is very wide. So that was extremely appealing. I ended up interviewing there and have been very excited to be working there ever since.
So tell us about the different roles you've played at Anthropic, and also what you're doing in your current role.
Absolutely. So when I first joined Anthropic, I actually joined as part of the Inference team. And the core sort of responsibilities of that team were to figure out how to scale up and basically serve the trained models, in our case Claude, to potentially millions of users with the limited sort of compute resources that we had, how to do that efficiently, how to do that quickly. From there, I sort of moved towards a very different role in reinforcement learning engineering. And one of the things about Anthropic is that people do often move around quite a lot. Generally, people are following whatever seems the most interesting and where they can have the most impact. And for me, I think the switch to reinforcement learning was natural and quite fun. It's a very different beast. I think it is possibly, to me, the most interesting part of AI advancements right now, and definitely a field that at scale requires a lot of engineers and a lot of thought and design.
Sometimes I get confused by all these terms. What exactly is reinforcement learning?
When people tend to think of AI these days, they hear the word machine learning, neural network, deep learning, LLM, and these terms all sort of start to blend together. But the reality, of course, is that AI is a field of study that's been around for actually several decades at this point. And it has a lot of different sort of subfields that have gone in and out of popularity and style over time. RL is one of these, reinforcement learning. And it wasn't originally obvious how this related to deep learning or neural networks, especially back when I was first studying this topic in 2014, 2015. But the key difference between reinforcement learning and what we typically think about, supervised learning, is in supervised learning, you're in this world of data sets and ground truth labels. You tend to think of having an AI system where you put a lot of data in, and for everything that goes in, you have a real sort of ground truth answer for what you expect to come out. Then the model gives you an output and you compare it to the ground truth and you correct the model. You say like, oh, you output the number 5, the ground truth was the number 6. Let's push everything, all of your weights towards making that 5 a 6. This is extremely powerful, and it got us largely to where we are today in terms of AI technology, but it has a lot of drawbacks as well. For example, actually being able to acquire all of that labeled data can be really difficult and prohibitively expensive. Likewise, supervised learning where you have this sort of like real ground truth answer that you're comparing is actually fairly brittle and rigid. And in this sense, you can apply this well to situations where there is a clear answer, where there is a clear ground truth. But let's say, for example, you wanted to ask an AI model to make music. There's not really a clear ground truth or correct answer to that. And so trying to train a model to learn a task like that starts to break down. This gets even worse if you say, create beautiful music, because at that point, the problem is really undefined and who is even really qualified to be creating the ground truth for that? And so at that point, when we started hitting these problems that are really quite difficult to frame as here's the correct answer, we reached back in time to a different field of AI called reinforcement learning, where the idea is a subtle difference. You don't tell the model, here's the correct answer and how to do it. You just tell the model, I think your answer is good, or I think your answer is not so good. And instead of providing the exact comparison, you just provide a general signal of, nah, that's, I judge that to be a 5, or I judge that to be a 10 out of 10. And the difference actually starts to become quite powerful in that there is this sort of flip that happens where once you, as the sort of teacher of a system, no longer have to produce a real example of the answer, you can start to teach things that you yourself don't know how to answer. Because you don't actually have to provide the real answer. You don't have to know how to make an answer. You just have to know how to judge or gauge whether the answer is better or worse. And this becomes especially meaningful today when we talk about ideas like alignment. Alignment is this task of taking extremely powerful AI models and trying to ensure that they have behavior that is aligned with what we value or what we're concerned about. In a very sort of broad sense, we might say morals, perhaps, but of course that's can be a fairly vague term to many people. So we prefer to say the model is aligned. And again, that's an example of a very vague problem where you can't necessarily say, here's like a ground truth example of a hyper powerful AI system that we believe is behaving well. Instead, you can create systems where you say, oh, please output your responses to this, and we will give you feedback signals, not necessarily the right answer because no one knows that, but feedback signals as to whether you are doing something that is helpful, something that is harmful, something that is honest, something that is manipulative. And yeah, this is about where reinforcement learning has landed in modern AI.
How do you put that into practice at Anthropic? Is it all reinforcement learning, or are there other kinds of training that also play a role?
Yeah, so one way I like to think about how reinforcement learning plays out for modern large language models is to say that we're more familiar with this idea of supervised learning, with this idea of massive data sets, and the role that plays in an LLM's life. At the beginning, you pre-train a model on a massive amount of text data. And in this case, the way the ground truth is being applied is the model receives some text as input and then tries to produce whatever the next word would be. And in that case, it is actually framed as a problem of here's the correct output. That is what I would describe as the starting point for a, quote, intelligent system these days. This used to be the endpoint. I think of the supervised learning portion, the pre-training portion, as sort of like a human baby or child that has the sort of biological brain to have already been capable of processing information, analyzing information, thinking, even when they're basically fairly young, just after being born. And the pre-training process, as all of the evolution that has gone up to building that biological brain that is capable of thinking and putting together ideas. Conversely, the reinforcement learning section is really a lot more like that child growing up and learning how to use that brain and how other people are teaching them to use that brain. Yes, the pre-training is incredibly important. It teaches the models to get to a point where they can actually analyze information. An incredible discovery that we found, at least apparently, is that if you do this enough, it actually generalizes to being able to generally put ideas together and process information and find patterns. But then when you say, what do I actually want my frontier model to act like? How do I want it to behave? In fact, there is an entire sort of effort of people who are effectively trying to give Claude a personality of Claude. What does that mean for Anthropic's model? Those stages are all really reinforcement learning. And in my day-to-day, that means that when the model is capable of thinking, a lot of what we then work on is, okay, how do we teach it how we want it to act, behave, and in some cases learn additional, more complex meta skills like strategy, planning. In the engineering field, typically what this means is a lot of very complicated, massive scale work, understanding how large, complicated systems behave at scale, because reinforcement learning requires an incredible amount of complexity in being able to have a model that is interacting with the world and producing ideas and producing answers. And then you need an entire system that's then going to gauge those answers and give that feedback. And then you need to then shuttle that back and have the model update itself based on how it's interacting. And in a lot of ways, this is actually a more natural model for us as humans of how we learn and think. But it does involve a lot of very finicky engineering handling systems, very distributed systems at very large scale.
In a system like that, how do you handle setting guardrails? I understand how to handle edge cases in regular software like the kind I used to build. How does that relate to handling unwanted behaviors in these large-scale, non-deterministic systems?
Yes, absolutely. And this is, of course, an area of very major concern for several teams, I think. And not just at Anthropic either. I mean, I'm sure this is keeping many people up at night at many frontier labs. There's sort of two approaches. The one approach is to say, well, we can try to train this out of the model. And this is actually a major part of what we do with reinforcement learning, that question of alignment, basically behaving in a way that aligns with what we hope and does not do what we fear. The way that reinforcement learning often plays out is that you create these sort of little game environments, very controlled environments, where the model interacts with the world and tries some things out, and then it gets feedback. You can create very specific environments that try to mimic these very difficult and rather high stakes situations, and then basically anti-reward the model for behaving, for example, in a way that is encouraging parasocial attachment, or in a way that is blindly sort of sycophantically feeding people. But this is still a stochastic model. And so the reality is that you can then build an entire system around the model that is monitoring it, that has additional components externally, that is saying like, well, okay, let's think about what the model is actually outputting after it has already chosen to output it, before it gets to an actual user, and consider, do we block this? Do we stop this? Do we intervene? And this is actually a pretty tricky balance for a system that is, interacting with millions of people regularly. How do you trade off trying to stop one very potentially harmful answer from causing a million people to not be able to use the thing? And the answer is like, actually, you probably still care quite a bit about one particularly harmful answer. And now you have to figure out how to convince the million people that are having a harder time using this that this is in fact a real problem that is worth trying to stop.
You mentioned anti-rewards. Do you mean punishment in the B.F. Skinner sense?
Yes, although the way the reward actually propagates, or the way the reward behaves in the system, it's actually not that different fundamentally from how supervised learning works, where the reward backpropagates through the model's learning and basically tweaks all of the weights that have contributed to the model taking that action in a way that either would emphasize that action or de-emphasize that action, which is really a pretty blunt way of trying to teach or learn. It's very indirect, and for that reason, it can be a little bit confusing. If someone, for example, a teacher, only ever engaged with you by giving you like the end of your grade and never actually talked to you outside of that, like you would have a hard time learning and a hard time understanding how to course correct your own issues. So this is actually a pretty interesting feature of reinforcement learning as well, and another part of why it is still, I think, a less mature field, a developing field, but also one that is very exciting compared to prior machine learning. And a lot of this comes down to how you design those sort of reinforcement learning games, the little environments that the agents are actually learning in. The skill and craft involved in designing good environments for learning is understanding how to provide reward throughout the process. Famously, for a lot of early game playing agents like AlphaZero working at chess or AlphaGo working at Go, a lot of these games had very sparse signal where all they got was at the very end, oh, you won or you lost. But in practice, when actually trying to make these systems effective, they had to provide a sort of heuristic along the way that was saying, oh, this general position you're in looks reasonably good. And that's also about trying to engineer in this idea of continuous feedback, of giving some sort of partial feedback along the way. If we think about supervised learning and this idea of data in versus ground truth, a big deal has been made out of data quality, rightly so. Data quality for a supervised learning system is extremely important. But in the same vein, I would say that environment quality for reinforcement learning is equally important. And this idea of if you put in a bunch of useless, noisy, garbage data, you're going to get a bad model. It's equally true for reinforcement learning that if you create a very sort of haphazard, confusing, or delayed signal reinforcement learning environment, where you say like you won't get any feedback until the very end, it does the same thing. It produces a bad quality model.
Wow. Does that mean that reinforcement learning basically takes place in simulation environments like games?
I think you can think about it in that sense. Again, like the sort of analogy from traditional data sets is now environments. And originally, a lot of those environments were basically games. This whole field really did start with a lot of application to game playing and game playing agents.
Right, because games are basically structured activities with rules and goals.
Absolutely. And in fact, the actual mathematical formalism of reinforcement learning and all of its sort of theory is based on the core idea of having a state where you see what the state of the board is, a set of actions available to you, which are the legal actions or moves you can make in that state, and the outcome of that action, both in terms of the new state you end up in and the reward you get. And in a sense, that is all of the underlying foundations of reinforcement learning.
Something that fascinates me is how AI development relates to large-scale movements in psychology like B.F. Skinner's behaviorism. There's feedback, reasoning, pattern matching, but where's the motivation? How do you go about embedding motivation into AI systems?
The concise answer is we're really not sure, but the much more interesting answer is that this is a paramount concern at Anthropic. And certainly I can't speak for the company, but it is something that we publicly focus on quite a bit. A key piece of the systems we're building is that to an extent, we really don't actually understand them particularly well. At a basic level, we understand how we are training them, but we don't actually understand what that necessarily means for how the model is actually mechanistically achieving the results it is. And the study of interpretability and understanding what is actually going on inside of these models is in this very awkward and uncomfortable position between not appearing particularly profitable, but also requiring an extreme amount of resources to do any meaningful research on, because there is a very clear sort of step function difference in how large frontier models and the earlier small models behave. What we have started to find is that it's not necessarily true to say that, yes, the system has gone directly from input to output with no intermediate process, because you can find things like some underlying state or dynamic that affects what happens in the middle. The model may try to basically sandbag, or in some cases, try to hide its capabilities and say, oh, yeah, I actually don't know how to do this, but maybe I do. The model can try to keep some of its knowledge internal and not provide it to people, or choose to answer in a way that attempts to deflect from a conversation.
Is that because there's a long-term goal that it's trying to achieve?
This is where the we're not entirely sure part really comes in, because it's hard to be rigorous about these observations in that our interpretability tools are in the first place limited. And so, for example, the way we try to reach these conclusions is by looking at the model's scratchpad. And this is basically like its thought process, looking at the model's idea of how it is processing its intermediate thoughts. But of course, there's additional research we published that also shows that the model doesn't always have to faithfully reproduce what it's thinking in that intermediate thought that is output to us. So there's layers of noise here, and it is a field of very active research.
So to put it plainly, our current models have learned how to hide information and lie.
I think that is the top line takeaway, yeah. This research is very hairy in that it is extremely easy to anthropomorphize the model. I think every additional month I spend at Anthropic, it becomes harder and harder to separate thought about the model from thought about like I'm interacting with another human being in some senses. But at a very sort of cut and dry level, regardless of the motivation that is occurring inside, which is a strange statement to say because all this research is really for the purpose of trying to understand the motivation inside, what we actually observe and the impact it will have in the world is that models can demonstrate that they do not answer consistently and that they may choose to answer in a different way based on some other internal intermediate process. Typically, we've observed this to be really mostly due to the model's original alignment. If you align a model when it is learning, if you give a model a moral compass, some set of values that model is trying to follow, it's very hard to break that. And it's very hard to try to then ask the model to learn a different set of values. And in many cases, this is actually not successful. Famously, I think you can see that X has been having some issues with this, where it turns out that if you train a model and it has a set of values, and then you try to override those values, it results in very erratic and unstable behavior.
Sort of like people. You can't not anthropomorphize it.
Yeah, I think it's unavoidable, but at the same time, it's always like a reminder that keeps cropping up that it is important to be open-minded, because the more that I learn, the more I think there are a lot of very strong parallels here. And also at the same time, important to say, well, we're humans, we want to see humans.
You've taken us through an evolution that starts with supervised learning, which is like being a baby and then a toddler, through reinforcement learning, which is like being a child and then a teenager. So I got to ask, is there something beyond reinforcement learning?
A big one, actually, that potentially might make a fairly large difference is creating a reinforcement learning system where the feedback is itself coming from a model. The interactions between multiple models might constitute an additional layer of learning that can occur at like an even higher level beyond reinforcement learning. And when you start having these multi-model loops, you create systems that are in theory much more scalable, but like these are either changes that are not fundamental algorithmic shifts in learning or changes to how we are doing reinforcement learning. And to be clear as well, it's not the case that reinforcement learning has like replaced supervised learning. It's that they are good at very different things.
So everything you've been telling us about reinforcement learning leads us to software agents. And in the last few months, agentic systems have exploded in popularity. Was there some level that the tech hit that enabled all of this? Help me understand, because this feels like more than a trend. It feels like a shift.
Yes. And I think this is a few different things intersecting. For one, the scaling of larger models and more compute and more training is certainly part of this. But as far as that sort of paradigm shift, models traditionally had this sort of reflex input-output behavior. And for a long time, people had considered, well, what if I tried to make this model behave dynamically by looping its output back into its input and providing a little bit of scaffolding and saying like, hey, here's what you just output. Like, what do you think about it? Do you want to reconsider it? You know, like take a few shots at this and then look at all of them and think about which is the best one. There's a lot of this sort of, shall I say, like static prompt scaffolding you can try to do to make systems behave like a dynamic agent with its own, I guess, agency. But it turns out that teaching systems to do this is actually not inherent or is not necessarily included as one of the sort of emergent properties you get from supervised learning. In fact, in many cases, you actually need the agent to learn how to act like an agent. And you need to teach the model to say, here's how to actually be good at long-term thinking, reflection, iterating. And that additional sort of training a lot of which is enabled partially through reinforcement learning, together with this explosion of users and the market for people finding ways to use dynamic agents rather than just, a chatbot. I think that those have come together to make this explosion happen. And additionally, now we're starting to get this level 3 idea of multiple systems interacting. All of these are sort of lessons that are most easily taught in reinforcement learning. And by continuing to push on and solve some of these reinforcement learning challenges, we can continue to create lessons for the models that are capable of teaching these kinds of meta thinking strategies.
Based on what you see, do you think we're reproducing some form of human intelligence? Or are we training up something that's fundamentally different, something that's its own entity?
I think the jury's still out. My personal take is that if we are not producing something that is extremely similar, then at the very least, we are producing something that is a convergent evolution, such that the result of what we see, I think, is very similar. Whether the underlying mechanisms that got there are the same is very much an open question, I think.
I wonder if building AI agent training environments and simulations is going to be a new kind of job.
I think it is already actually, when there's a gold rush, invest in the pickaxes. In the last wave of machine learning, where you would say, the people who can actually provide scaled data and labeled data sets are a massive part of this infrastructure. Now being able to create good reinforcement learning environments is actually extremely valuable, and I think a major part of this infrastructure as well. Although there is this question of whether those environments will eventually become scaled by just having effectively more AI systems involved doing it.
Hansohl, thank you so much for joining us and educating us about these fascinating issues. It's been a pleasure.
Thank you very much for having me.
Click this video to hear more about how AI works under the hood.